Hi everyone, welcome to the sixth seminar in this Causality lecture series. Today we'll be speaking, make a shift towards the Pearlian framework, and we'll speak about interventions and also about structural causal models, causal Bayesian networks, and mostly about defining the framework. Karthikeyan.
Yeah, so finally today we'll start with the Pearlian framework. So it will be full of graphs from this point on. But before that, I'll just put a small break just to recap what we have done before and just to motivate why whatever we have seen so far is not the full picture, at least personally, according to me, having worked in this area for long. There are lots of things that the Pearlian models imply that's not very at least obvious from the potential outcome framework, right? So let's start with that. So the recap is for the first 4 to 5 lectures, we saw potential outcome framework. Now, I just want to point out certain things that we saw, not the whole summary, just so that I can motivate what I'm going to say. Okay, like we look from the Pearlian point of view. So the definition of a potential outcome was essentially not constructive in some sense. It was as though there are 2 other columns in your table. And the notion of an intervention essentially was captured by simply the consistency. You remember, we had 2 imaginary columns. We said one column is when you treat someone, the other column is when you don't treat someone uniformly. And then depending on the treatment, you just basically put the values from one column or the other column. So essentially, that was an equation, right? And the second most important thing to do all this observational analysis was this ignorability, where you basically said these 2 imaginary columns, right, is independent of the treatment conditioned on the set of covariates. So again, this is not going to be testable. So one could say that, okay, can you actually, from ab initio, define what an intervention is, like specify as a definition, construct it, right? All I observe are distributions. You intervene, I observe distributions. If you don't intervene, I observe distributions. That's all I observe. From that, you might want to actually construct a model that is consistent with the notions of causality and intervention. Okay. So, I mean, it's not a criticism, but rather I would say this is a different view, a very empirical view. This is a data set that you're given and you're asked some question. How do you go about answering? So from ab initio, if you think about it, this is a very good approach, and historically, it has actually been very, very useful in practice, right? But I think causality is a bit more than just this. So as a as to motivate that, I would go back to my first example about the sure thing principle, right? The sure thing principle basically said that if a condition is to be caused by your decision, you really need to think. If it's not, then at least the sure thing principle is reasonable, right? So it gave some sort of a criterion based on some ordering amongst variables. So it has a natural sense that something actually came before something else. So this notion of ordering is very, very crucial from the sure thing principle. So let's actually try to get some rough desiderata. There is no axiomatic way of deriving whatever I'm going to say. I'm just going to introduce the model. But the good thing is, if it captures most of the intuitions that I'm going to say, then it's rather a good causal form. I'm not saying this is the only unique one. Maybe there are slight variations of Pearlian models that you can think of that would still satisfy a lot of these things with very minor, very subtle differences. Okay, but this is a very canonical one. So, but what the sure thing principle tells you is that at least for decision making, you have to understand a notion of causal ordering, right? So this is very, very important. So that's at least, but that much is at least clear. There has to be some ordering amongst variables that you observe, and what comes later and what comes before the notion of causation is related to this order. That's what the sure thing principle said, okay? Or the violation of the sure thing principle said, okay? So the second thing comes from a very, very different viewpoint, more from a classical physics viewpoint, okay? So when people were trying to figure out whether the quantum phenomena that they measure is indeed quantum or not, so there was a question as to, okay, you have two photons, you couple them in some way, and then you separate them apart, right? And then you try to measure one, and you force one sort of a measurement on one, which is basically, let's say you measure this to be one. Then turns out that this flips with very high correlation depending on the original wave function. So this was the physics view of quantum. I mean, this was one of the main tests that people use. Now, how do you know that something non-classical is happening here? That was a question amongst all physicists. I mean, you derive all this Schrodinger equation and all that, and you try to explain the data. But the most important is, can you give me a test that would distinguish between what is classical and what is not classical? So this was something that physics people always worried about, right? And so we all know that there's this famous experiment that was proposed by Bell. It's called Bell's inequality. There's an inequality that he derived, and then which was used to distinguish between quantum phenomena and everything that could be possibly classical, right? So what does it mean that you have an inequality that separates everything possibly classical versus something that is potentially quantum, which people actually can verify today experimentally, right? The key thing, I mean, relating to causality is that the way they actually defined all classical theories is by using a very fundamental principle in causality called Reichenbach's principle. Okay, it is so important that it plays a very, very important role in something as fundamental as Bell's inequality. Right? I mean, do you know if anything quantum actually happens? Because there are Bell's experiments. And Bell's experiments tries to verify Bell's inequality, right? And what is the fundamental principle that allows you to actually separate the quantum from the classical in the first place? It's basically what is called the Reichenbach principle. Reichenbach's principle is very simple to state. It says, if you measure two things, two variables, x and y, and if you ever find a correlation between them, there are three possibilities. One, x causes y, which means if you intervene on x, y will change. Or y causes x, it means if you intervene on y, keeping everything else the same, x will change. Or there is a common cause, which you condition on, x and y will become independent. Okay? This is a very fundamental principle that was used to test Bell's inequality, something so fundamental in physics. Okay. So why is this principle so important? Well, all of classical theory, or all of classical physics, everything is all about some hidden variables P of u, and then some joint distribution between the observable variable x and y given q, right? Now, causation is really about, I mean, the integral over this is what you observe as the observed correlation. So what it says is that you can either have x causing y, y causing x in actual reality, no matter what u is, basically, or you can actually have p of x given u times p of y given u, and you could still integrate conditionally independent variables, and you can still get a correlation, right? This is a very fundamental principle. So in physics, always you observe something, and you try to construct a causal model for what you observe, basically. It's a law. It's a law. I mean, there's no proof. It's considered to be something so fundamental that it was used as a test to distinguish between quantum phenomena and causal. The way they did is they basically take the photons, they couple them, and they take them very, very far apart, such that even light cannot reach very fast. Okay. Then they try to measure one. They'll see an immediate collapse. They note the clock, and if it travels faster than light, then there are two. Then one of them has to be false. So one is Reichenbach's principle must not be true, or relativity is not true. We don't know which one it is. I mean, that's a very simplistic caricature of Bell's inequality. It goes into very deep philosophical discussions. I don't want to get into all of that. But this criteria was super important in order to distinguish between quantum phenomena and classical phenomena. Now, look back at potential outcome prediction, right? In defining causation or intervention or even counterfactual, was there a place where you could explicitly either derive Reichenbach's principle as an implication? Probably not. Or was it crucially used in any particular way? Probably not. right? Maybe indirect ways there was indication that Reichenbach's principle is probably true, but it's not like you have a theory where Reichenbach's principle is implied. At least people consider this to be a very core principle. Therefore, whatever causal model that you have must at least directly imply Reichenbach's principle, at least with some reasonable effort. Okay. And the other thing is a related fact about Reichenbach's principle is that if I define a model, it must imply this rule. I mean, if I define a bunch of distributions and definitions, in that definition and whatever the notion of cause I have, that must satisfy this. That's all I'm saying. Right? Yeah. But the definition of cause is just my own divination. Okay. So I'm not going to derive that again axiomatically from something. There are some very interesting recent results that points out to something very deep. But we will, that was even asked by Mihir today before the class. I go into that if I have time related to definities theorem and all that. But before I go all the way there, this is a very simple requirement. What I'm saying is, if there is an observed correlation, either this can happen, or X can cause Y, or Y can cause X in the interventional sense. Now, you might say, is it possible to actually define interventions first, then imply, and then have a definition of causality, or causality first, and then have some definition of intervention? It turns out these two are very, coupled concepts. Okay, usually people define, I've only seen people define it together. Never as one, then this becomes like an implication. Basically. It's unfortunate, but that's what it is. Okay, and if you actually read about Bell's inequality, it's a very fascinating thing. They went to extreme lengths to verify Bell's inequality, and you will actually see how much they cared about the Reichenbach's principle when they actually established all those experimental conditions. So it's not just a principle that is loosely used by some theorists. It's a very serious thing that experimentalists take it to be the hallmark of classical physics. Okay, so at least whatever principle that you come up with must satisfy this Reichenbach principle. So that's one other motivation. The second motivation is again related to Reichenbach's principle, is that there's this notion that, let's say I have one measurable variable regarding what I'm going to say next, or this particular hall in IISc here, right? Let's say I have some other department somewhere, like very far away, maybe at the other end of the campus. Let's say I have a measurement over there. Okay, I can record both and look at it in a retrospective manner. Now, the distance between here and let's say the other thing is like 2 kilometers or something. Let's say I measure them very, very close to each other, almost at the same instant. Right? Do you really think there is any causal relationship between this and that? Like from intuitive physics. I can make the time interval as close as possible. So if I make two measurements so close in time, but far apart in space, we have an intuitive notion that whatever is happening here in this hall is not immediately affected by anything that is currently happening in whatever distant hall that is in IISc.
I think Einstein's theory is molecule.
Yeah. So that is exactly what they tested with the Reichenbach. So the point I'm trying to make is that locality is a very, very important feature of classical causality or classical physics. So one thing it says is that when you observe some correlation afterwards, X must have caused Y must have caused X, or there must be a common cause subject to which these two are to be independent. But it doesn't say anything about whether it could have caused or not other than this particular statement. It just says there are three possibilities. That's all it says. Right? Now I'm going even further. I'm saying, let's think of a thought experiment where there is an event I'm measuring now. Let's say on every day I come and lecture in this hall. At 5 o'clock, you make a measurement. And at 5 point blah, 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 0.00001, you make some measurement at the very distant end of IISc, so that light can't travel. Right? Do you really believe that there is any causal relationship between them? Of course, you can't mathematically answer this question. All I'm trying to say is that it's an intuitive notion that there has to be some locality to cause and effect relationship. Every single variable cannot be affected by everything else in this universe that's being measured currently. That's just not possible. So there has to be some sort of feature selection. It's intuitive, right? If it's not, then you're basically saying everything can instantaneously cause everything else. So it means by definition, by some constraint of physics, if you believe in relativity at least, you must believe that there is some locality, at least in classical physics. Let's forget the quantum. So locality is another important attribute of cause and effect relationship. So I basically said three things. One is there is some implicit ordering because the sure thing principle requires it, and in practical situations, thought experiments very clearly say that some sort of ordering matters. The second thing says that there's something about Reichenbach's principle, which is when is an observed correlation justifiable, right? And the third one says, okay, if there is a causal relationship between X and Y, can it just be arbitrarily between any two variables? Probably not in real life, right? So you ideally would like an abstraction that at least captures these three. Yes.
So you said there are 3 points to Reichenbach's principle, 3 cases. This is one of the cases.
This is one of the cases. The other case cannot be expressed probabilistically. That is a problem. It just says something about this conditional distribution. It's joint, but it means that X causes Y. Probabilistically, I cannot explain that yet. But I'm intuitively saying that X causes Y means if I change X, then Y will change. Y causes X means if I keep everything for a given U, like everything in the universe is fixed, and I just change Y, then X alone changes, basically. So that is Y causing X. That's my simple definition. Right? Now, this principle, you may believe or not believe, that's a secondary matter. Right? But what's important is that it distinguishes classical physics as we know it from quantum phenomena. So this is a very fundamental principle of classical. Then locality is another important thing. It's also related to Reichenbach's principle because they want to test non-locality also. So they are either saying it's non-local or it violates Reichenbach. Right? Both of them are a problem for classical physics. So which means whatever we think of classical physics definitely includes both these principles. So you ideally want some theory that actually captures all three. Okay, I'm not saying that Pearlian theory is the only thing that captures all three. There are aspects of this hidden in potential outcomes when I was deriving certain expressions, possible. But there's a more explicit definition that would directly bring out all these three principles, right, from the direct definition. So that's why we are going to study Pearlian models. I mean, at least that's my personal motivation why I would look at Pearlian models, even if you gave me potential outcome. As a broader theory that actually captures some intuitive things about classical causality. Any questions here? There's nothing I've said that's axiomatic or nothing provable. I've only claimed these three things, and there are enough experimental evidence for the second Reichenbach principle. The first one is known to be a fallacy in logic, because logicians actually concluded some stuff about sure thing principle just showed in the first class without ordering. So we know that ordering also matters for addition. Okay, so that's as good a motivation I can give about Pearlian models. Let's actually get into the definition. Yes.
Is this how they motivated?
No. Okay, so the real history, I think, is so there was in 1924, there was an epidemiologist or sociologist. His name is Steve Wright. This way. Maybe 1920s, I don't know the year when the first thing appeared. So he basically wanted to model for some sociology study, some cause and effect relationship between some things in human behavior as measured. And the way he started writing these things is that he actually started writing functional equations, relating them to this. But then he said the left-hand side and the right-hand side are not like equality things where you can start interchanging both. When you intervene on something, the left-hand side is set to some particular value. So he actually defined what's called structural causal models for the first time. Okay, but it was not a formal theory. It was not related to probability and all that. I think Pearl and Verma and others in 1985, I mean, I won't say exactly 1980s, late part of 1980s, they were actually studying Bayesian networks for inference. It had nothing to do with causality. Then they realized that the same language is implied by structural causal models. Okay, but there's a difference between a Bayesian network and a causal Bayesian network. So let me define what a causal Bayesian network. The Bayesian network is first, and then let's go to causal Bayesian. I'm just mostly following Pearl's book. but in random order, depending on what I believe would make sense, like for you guys. Okay. That answers the question. So this is the beginning of structural causal model. I haven't introduced what that is yet. So let's go to structural causal models. Okay. By the way, I just want to make it very clear that I will start from structural causal models, but that is not necessarily the starting point. What I mean is, you don't necessarily need to have a structural causal model in order to do interventional study. It might come as a surprise to you guys, but they are not equivalent. You only need what is called a causal Bayesian network, and that's a complete description of what happens interventionally. Okay, you don't need anything more than that, basically. However, the structural causal models can help you model counterfactuals. Okay, there's a very big question that often my collaborators have asked me. If there is a causal Bayesian network, can you prove that there is a structural causal model from which it is derived? I don't know the answer to this question. Okay, it's a very deep question. It just basically says that any causal Bayesian network, the way I'm going to define it soon, has to be derived from some structural causal model. Okay, that's not obvious at all. Okay, so structural causal model will be a physics description of reality, and that implies a causal Bayesian network for sure. But whether all causal Bayesian networks need a structural causal model, well, that's not really a very easy thing to say. Okay, and we don't even know at what sense you can prove that in the first place.
If the functions in the SCM are stochastic, then it should be equivalent.
No, but causal Bayesian network is all about a set of distributions. That's all. Why should that be derived as some functional inequalities relating some unobserved variables and these things? There's no reason to. In fact, the treatment will be like that. So we will define Bayesian networks, then we'll define structural causal models. And structural causal models do imply causal Bayesian networks, but the other way, nobody knows. Like any,
there might be a trivial SCM, which is 0, 1, which.
No, but the question is, it's an epistemic question, right? Like whenever you measure a causal Bayesian network in the real world, like does it imply that it has to necessarily have some structural causal model along with it? Why do you have to invent all these exogenous variables and functions that you don't see or you can't measure? Why should they exist in the first place? Right? So we don't know. In fact, it's not unique. We know that for a fact. If you define a causal Bayesian network, sometimes the structural causal model is not unique. Even if I define all in my interventions, it's still not. Okay, I can give you a very simple example, but that I'll do it later. So there's something about counterfactuals that is very, very related to structural causal models. It seems that you can define counterfactuals only under the notion of structural causal models. But interventionally, to an extent, you can actually deal with everything at the distributional level. You don't really need the notion of structural causal model. I mean, you can use it if you want. You want to prove something, maybe you can prove only under this assumption. It makes your proof easier. Yeah, sure, you do all of that. But what I'm trying to say is, from a very fundamental point of view, all interventional questions can be answered with Bayesian, causal version of Bayesian network. And I tell you what the difference between the normal Bayesian network and causal version is. And then, in order to define what a counterfactual is, at least in the Pearlian world, you really need to know the functions or your model of the functions. I mean, counterfactual is never a set thing in reality. I mean, everybody has a counterfactual for the same question I asked you, depending on your conception of how the world works, right? So, but the most important point is that in order to define a counterfactual, you need to go one level higher. Distributions are not enough. And I'll sort of deal with all of that. But let's go to the interventional level, because the previous thing was how do you estimate interventional effect? And there's this mysterious thing called ignorability. When is it true? When is it not true? And how is it related to all these eigenvalue principles? We will actually flush all of this out. So that'll be the next 2-3 lectures. Okay. Okay. Now let's define what a Bayesian network is. This is nothing causal. So let me call it non-causal Bayesian network, just to make a point that there's nothing causal here. What I'm going to say first, and then I'll go to causal Bayesian. Okay. Okay, so just for clarity, let's call it causal Bayesian network, the non-causal Bayesian. Okay, so you have a joint question. So you have a joint. So you have a set of variables V. We'll always denote it as x1 till xv. Okay. No, maybe be careful. If I choose the notation, I have to stick with it. I'm trying to figure out. I think maybe the easiest one would be. Okay, I'll actually use x1. And I'll make the treatments to be P's, just to be consistent with the potential output. But that's not how people use it in the Pearlian world. So I have to translate all the time. Okay, so this is a set of variables you observe. That's all. There's a joint distribution, right? So you have P of B. This is nothing but some joint distribution. Okay. Now, first thing, ordering. Pick any ordering you like, right? Let's pick the ordering 1, 2, B, right? You can always factorize any joint distribution as a product of conditions. There is nothing complicated over here. So I can have I runs from 1 to B, probability of xi given everything till I minus 1. So I'll just denote it as I minus 1. Right? So I've ordered them 1 to B, right? And every variable, I mean, say it can be factorized as the conditional probability of xi given everything before. It's all this, right? And by the way, so all the treatment will go through discrete variables. That's one of the reasons I asked that question. I don't want to go into all measure theoretic thing, trying to define conditional expectations, conditional distribution. That's a different course, right? So here we'll only do discrete variables, but all that I say can easily be implemented in continuous variables too. I mean, if there is any difference, I would most likely try to endeavor to mention it. But most likely, whatever I say should hold in the continuous case too. But it's very easy to work with discrete variables, or just work with discrete variables. Yes.
The continuous case, these are just densities.
Yes, these are densities. This will be a density. This will also be a density. But then I have to worry about when conditional densities exist. There are some regularity conditions. I'll go to Lebesgue theory and all that. I don't want to go into all of that. Just make it very simple. If everything is absolutely continuous with respect to the Lebesgue measure, I think everything is fine. You just replace with random Nicodemus derivative, you take the product, then you're done. Right? So there's nothing complicated over here. But then if you consider this crazy continuous discrete mixtures or some weird continuous distributions that are not absolutely continuous with respect to Lebesgue measure, you have to be very careful about handling those things. But I don't want to go into all of these pathological things. This discrete variables makes the theory simple. We want to prove other things using conditional independence and not necessarily deal with measure theory. Okay. So there is an ordering. So we've already captured ordering, but it's an arbitrary ordering. There's nothing causal about it. And we'll come to this point exactly later. Okay, what's the next thing you want to incorporate? You actually want to incorporate locality. So what I'm going to say is that there is a DAG. Now, G is a partial order, right? Any DAG is a partial order. Now, G, first of all, respects the ordering 1, 2, 3. This is for simplicity. I mean, it could be any other ordering. But since I picked this ordering, I want the DAG to be consistent with this ordering. That's all, right? But now for every variable I, let's call it xi, I actually have parents PA of I. So these are the parents, right? And the parents always come before in the order. Okay. Now, it could be the case that the distribution that you're dealing with is somewhat compatible with this DAG, and by which what I mean is that by definition, the same thing can be written as the same product, but the conditional distributions don't depend on everything before, but it only depends on a subset of your ancestors. Okay. This is not a proof. This is just an assumption. Okay. In the more general case, your PA of I will be equal to xi minus 1. So I'm not using any generality here. I'm just introducing something more general, like more granular, right? We have incorporated the assumption of locality. So we are just saying that not every variable is dependent on everything that happened before. It is only dependent on a few things.
You mean the partial order respects this order?
Okay, so for example, so if you have a graph like this, 1, 2, 3, 4, right? The partial order is 1, 2, 3, and 4, right? But it respects two orders, 1, 2, 3, 4. It also respects 1, 3, 2. So both are consistent with this order. I'm just picking one G, and I'm just claiming that according to that G, this distribution factorizes. Okay. Now, if this happens, this is a definition. There's no proof over here. This is a definition. This essentially means that P satisfies local Markov condition with respect to G. Okay. All I'm saying is that there is some ordering. You take a G that's consistent with the ordering, then I sparsify it in the sense that there is a sparsification. So it means the joint distribution does factorize this way. And the moment I say it, I'm just saying that P is Markov with respect to G. That's all. This is a definition. Okay. Okay. Now, what's the first implication? So we'll call. So we just use shorthand notation. We'll use it again, many times, probably in the next few lectures. So P is LMC with respect to G. Right, this is what I'm going to write. This is a relationship. Okay. So the probability distribution is going to be locally Markov with respect to, locally Markov with respect to G. P LMG essentially implies that locally Markov with respect to G. And I mean this factorization. I don't mean anything else. All right. So the first simple implication is that if P is locally Markov with respect to G, then the following conditional independencies are true immediately, ab initio, which is xi is conditionally independent of all non-descendants of xi conditioned on the parents. Okay, so let's go to this graph. 2 is the variable I care about. 3 is a non-descendant. Okay, and all I'm saying is that 2 conditioned on 1 is independent of 3. Okay, so the example graph. So this is the example graph. 1, 2, 3, 4. The example is that the probability that x2 is conditionally independent of x3 given 1. It's an example of this set of rules, right? It's very easy to verify because of the conditional ordering. Just marginalize with respect to everything else. Only this conditional distribution remains. Whether you have other descendants or not, you can always marginalize with respect to them. Maybe the same conditions, right? So you can verify this. It's not very difficult to verify. But the key point is the moment you assume factorization, it immediately implies local Markov condition. Okay. Okay. Now, by the way, this is a set of, so you can take any subset, right? And then this will still be true. Any set of non-descendants of xi will be independent. The moment you condition on parents, you're basically sort of decoupling it from every other non-descendant. By the way, I'm not saying that x2 is independent of 4 given 1, because 4 is a descendant. I'm only saying from non-descendants, right? So some people call this, I think there's a name for it. I don't know what it is called. It's maybe called parental Markov condition or something. Basically, it's a conditional independence version of this. But by the way, this only has factorizations. Okay. This one is a bit more. So this already implies quite a lot of conditional independence. The moment I impose locality, I already have this. Okay. So that's the first important thing. Okay. Now, what about Ryan-Bach principle?
parents of U is
I
parent
took
of
all the causes out, and Xi and non-descendants don't have an edge between them. They don't even have any directed path between them, right? At least Xi doesn't have a directed path to the non-descendants. So the moment I condition on all the causes, they actually become independent, right? So this is saying there's a set of common causes, such that condition on them, I've actually made two things independent. Okay, now here, just want to say one more important point. 2 and 3 are correlated because there's a common guy over here. So they are actually correlated. So there's already Reichenbach's principle that's sort of popping up right just in this particular thing. So there's no relationship, causal relationship between Xi and non-descendant in one way, essentially. And therefore, you're already looking at common causes for which you can actually make them independent. They're not exactly common causes, but this holds essentially.
Non-descendants does not include the parents.
Non-descendants, even if it includes the parents, because you condition on the parents, will be constants. So, for example, Y is always independent of a constant. I mean, this is like an axiom. I mean, take this to be a condition of an axiom. So you always take one random variable to be independent of constants. Since you condition on them, even if you include parents, it doesn't matter. I mean, that's the definition. Right. Okay. Is there any other questions?
This is one of the conditions of not all.
Not all. Yeah. Now, what you could do is, okay, there's a direct implication. So because box, take Xi, which does not have a directed path to Xj. Okay, or the reverse symmetrically. All I have to show is that there is some common causes conditioned on which they both will become independent. I have to show you this, right? It's very simple. Xi is always independent of Xj, conditioned on the parents of J, comma the parents of I. It's always true. Okay. By the way, one cannot be a parent of the other because I excluded all the directed paths, right? So suppose this doesn't exist and this doesn't exist. This is automatically true. You just have to apply this principle twice in the appropriate direction and you will immediately, because once you condition on the parents, they are independent of everything else. So this guy is protected from every other non-descendant, and this guy is protected from every other non-descendant. There's no way they can talk to each other, right? So Reichenbach's principle is implied over here. So I started with three things: ordering, locality, Reichenbach's principle. Now you might ask, I didn't introduce causality yet. Already by just looking at these distributions, I already seem to satisfy all of these things, right? But remember, the ordering that I picked was arbitrary, and locality that I picked was just a factorization. If you want to make it causal, you need to go a little bit further, and I will tell you what other conditions you actually need. But the point is that it's going to be some sort of a causal version of all these things that actually implies the Reichenbach. But I haven't gone to that yet, so I'll just keep it aside. But we are already incorporating the three important things, and then you sort of start seeing that the moment you assume ordering and locality, essentially Reichenbach's principle. At least in this. I haven't done anything. I just taken joint distributions. I assumed ordering and locality. Automatically, there is some version of Reichenbach's principle. But remember, this is not quite Reichenbach's principle. I'm not saying anything about causation here. I only said in your factorization, there shouldn't be any directed path. But for this to imply that X is not a cause of the other or that is not a cause of this, I need a different definition. And I'll come. I need one more definition. Is that clear? So this is not exactly Reichenbach. Just be very clear. Let's call it observational Reichenbach principle. I am not saying that I am excluding the causes. I'm only saying there's no directed path. Right? And then this is automatically true. So now that you actually have to just fix this part, that non-existence of directed paths must imply no causality. That's the only thing that you need to make sure. The moment you make sure, essentially you have captured all of this. But it doesn't necessarily mean it's complete. We will come to that. But this is automatic. Yes.
So I'm just trying to recap. We started with an ordering over vertices, picked some G with respects those that ordering.
Yeah.
Then is this claim for that G? Or
it's that G, that G. That's why I said directed paths with respect to G.
Not for every graph that satisfies the ordering.
If you have a bunch of graphs for each of which this is true, even with respect to each of which all of this will be true. The question is, are there multiple graphs? That's a different question. We'll come to that. Yes.
So based on what ordering we do initially, we have a graph. So there can be many graphs for
Yeah, correct. That is true. So that's the next set of equivalence classes. Okay. So you already saw that P being Lm with respect to G. That's it. Sure. Yes.
So we took that as defined, which is to say local Markov.
There's a distribution that satisfies this factorization. That's all I was saying.
In the real condition, when is that?
There's always some factorization. The only question is G is dense or not. P is always Markov with respect to some G. The simplest G is complete graph. All P's are Markov with respect to all tournaments. Okay, so there's nothing complicated. But the thing is, if you have a tournament, there is no sparsity, which means you can't make any set. There's no non-descendants. Everything is everything is connected to everything else. So there is really nothing you can say which is non-native. Because the moment you take all non-descendants, all the non-descendants will be already part of PS because they'll all be ancestors in the tournament. So this is basically vacuous for a tournament. The moment you start having sparsity, which is some sort of non-trivial locality, that's what I mean here, then you start getting non-trivial conditional dependence. It's sort of inevitable. There's really nothing you can do to stop this. The moment you assume that, then this is all true automatically.
Then given any P, there might be multiple G's that satisfy the.
Correct. We will call to what? So given that you asked, I maybe need to introduce another terminology. So there are a set of conditional independencies implied by the graph. That's essentially all I'm getting to. But there are conditional independencies that you observe in the data. Okay. Now, when the set of conditional independencies implied by the graph is a subset of independencies that you observe in the distribution, then this distribution becomes Markov with respect to this graph. That's another way of thinking about it. So that way, if you take the complete graph, any distribution is Markov with respect to that. Why? The set of conditional independencies implied by a tournament is nil. And that's always a subset of any set of conditional independencies. Therefore, any distribution is always Markov locally Markov with respect to the tournament. Any tournament. That's clear, right? But you can say only non-trivial things only if there is some non-trivial locality. Otherwise I can't say anything. Okay, now there's a very big theorem, very fundamental. So the key point is that I only started with the factorization. I immediately started getting non-trivial conditional dependencies and even more. Okay, so then the question is, how much more are there? And how many more conditional dependencies can you actually sort of definitely say that it exists? Okay, so there's something called deseparation. So it's a graphical criterion. Okay, so there are more general versions of the graphical criterion. For whatever I'm going to discuss, the scalar version is sufficient, so I'll just go with that. But you can make some of them look to be subsets. Okay, that's all there is differently. So I'm going to tell you when X and Y conditioned on Z is true over all P that is locally Markov with respect to G. Okay. Now, I have a given G with respect to the tournament, all distributions are locally Markov. Now, what are the conditional independencies that are necessarily satisfied? Well, I can't say anything. Maybe there are more, but I can't guarantee anything at all. Okay. Now you give me more information. You say that, okay, there's a sparse graph with respect to which my distribution is locally Markov. Now, that's all you have said. You haven't said anything about the distribution. You haven't said anything about joint distribution, nothing whatsoever. But over all P that is locally Markov with respect to G, I can now tell you what all conditional independencies are true. And that is characterized by what is called the deseparation criteria. It's very, very important that I am not claiming these are the only conditional independencies that are true. I am only saying if you take all distributions that are locally Markov with respect to G, then it characterizes the set of conditional independencies. But if you have only one distribution, only one direction is true, which is the deseparation implies deseparation implies conditional independence. So just not to confuse you, I'll write two theorems, just to be very clear, both sides. I haven't introduced what deseparation is, but it's fine. I will introduce shortly. Right. So the theorem 1 is very simple. P is Lm with respect to G. Then deseparation implies Ci. That is some x, meter y, g. Okay. Now theorem 2. If for all P, Lm with respect to G, if Ci holds, this actually implies deseparation. By the way, this version I think has been proved only for discrete random variables because if you want to prove it for other things, it's a bit complicated. That much I'll say and stuff. Okay. Now, 2 is a bit complicated. I won't prove that. 1 I will prove, but not now. I'll prove in some other lecture. The most important thing is to develop more intuition about deseparation and relate it back to the treatment effect estimation problem and then the causal gradient. That's probably the more important thing. But this is a very important thing. Now it was proved, I don't know who proved it first, but Verma 1988 is a paper that actually specifies these two results. Okay. Yes.
Sorry, deeply mystery. What is Z with respect to?
Z, these are all subsets. Like X belongs to B, Y belongs to B. Z is a subset of observed P. So P is locally Markov with respect to G. Whatever I'm going to say, which I have not said yet, implies conditional independence. And over all distributions in G, if some conditional independence holds, then it implies deseparation. Yes.
What do you mean by so conditional independence? There exists some X, Y, and Z such that condition. Some at least.
Yeah. This is a specific condition. So there's some variable B belonging to this, some variable belonging to B, some other subset belonging to C, such that I test this conditional independence with respect to the B variables that I have.
When you say that X and Y are deseparated with respect to
Z, yeah, that's what it is. Yeah, I'll come to it. Okay. Now I'll just give you an intuition about what deseparation is because it itself is a more complicated thing to say if you're not introduced to it first. So I'll do that and then I'll go and connect it with everything else. It's very, very important to prove what's called the backdoor investment. I'll come to that. But so far, is this clear? Most important thing, this is per P. So structure implies conditional independence. That's for all distributions. But the reverse is not true. Okay, the reverse can only be certified over a family. It cannot be certified with respect to one distribution. So there's this notion of faithful distributions, and again come to that later. So for faithful distributions, it simply means that you consider distributions where the reverse is also true, right? Then that family is called faithful. Okay, and it turns out the subset of faithful distributions is measure 1 over an appropriate parameterization of joint probabilities for discrete time. Okay, so you're not missing too much in the reverse direction. But I haven't told you in what sense, but we will come to that later. Yes.
The reverse direction is sort of can be appreciated when you take G as the complete only. So you could, every distribution is locally Markov with respect to G. They can give you.
But no conditional independence holds universally throughout, and therefore, yeah, it means not this. Correct. Perfect. I mean, that's a corner case.
Yeah.
Yes.
So just trying to understand the theorem one. So it says that for all G that satisfy the problem,
The other way around.
for all P that satisfy a particular G.
No. There exists a P that is locally Markov with a specific G. If D separation holds with respect to G, then this holds with respect to P. Okay, but only for all P that is locally Markov with respect to a specific G, if Ci holds for all P in this family, then D separation is implied for this. So here you consider all distributions that are locally Markov with respect to a G, and then you go for each of those distributions, uncountably many, you keep checking conditional independence. If one conditional dependency using this subset holds universally, only then it implies D separation.
Why did you say there exists P in the first case? It should be for any P between.
Yeah, I just said, I mean, if there is a given there is a P that is locally Markov with respect to G, then that's all. Okay, still not causality yet. Okay, so let's go to D separation. I hope I would reach that by the end of the day. Otherwise, I'll leave you hanging. Because if I prove that, it will be another 30-40 minutes, probably even much longer, which I will come to. But what's more important is what you can do with these results. Right, so let's go forward and let's see that. Okay, so what is D separation? So here it's all intuition. This is very basic graphical models theory. It's got nothing to do with causality. So the moment you have some P which is locally Markov with respect to G, D separation is the following criteria. So we denote D separation using D. Okay, there are three variables. So X is D separated from Y given Z, or Z D separates X from Y. Okay, so X is D separated from Y. Okay, so before we go into, so the definition is a very complicated one. So before we go into the definition, let me give you some examples to get you an intuition of where this definition actually comes from. Okay, now let's take three variables, A, B. Let's always assume, so then there is C, and A and B are not connected in the graph. Okay, there's an edge between them. I have not told you what is the orientation. What are the possibilities? So you can have an arrow like this. You can have equivalently in this way the mediator, or it's a common parent, right? Or it's a common child. Okay, there's one remarkable thing that separates three of them from the fourth one. That's where everything starts. Okay, what is the condition? You can observe that A, okay, so let's take all these three. You can easily observe that A and B are correlated. Okay. I mean, there are ways to make them not correlated, but the point is, generally speaking, if you have something like there's a strong relationship, then A and B are generally correlated. Right? But the most important thing is A is independent of B given C. The condition on this, you have a mediator, so if you condition on the middle one, the other two become independent. So basic information Markov change. Right? Similarly, even if you have a common parent, the same thing is true. The common cause, so condition on it, A and B become. Okay, I'm just taking only three variables. Now you have A, B, and C. Here alone things differ. Basically, what happens is A is actually independent of B, but A actually becomes dependent on B given C. Right? So if I did these two conditional independence tests, and if I somehow knew that A and B did not have an edge, I can basically figure out whether the orientation of this kind or of this kind. Okay. This has a lot of names. It's called the unshielded collider. immorality and all that used to be some things that people say, but let's forget about all of that. This is an unshielded collider. Okay, you cannot, if A and B had an edge, I can't say anything about it because first of all, A and B are not independent first, so then I can't say anything. If this conditional independency is true, then if you check for this, then it's an unshielded collider. Okay, but it's the flip over here essentially. Okay, now essentially all you need for defining D separation is just these three. Okay, because in any path that you take in a graph and you consider triplet by triplet, it's a non-trivial path, meaning it's not just ending in an edge. If it has even one more entry, it will have to follow this pattern or this pattern or this pattern or this pattern. Okay, intuitively, if I have this pattern, if I don't want A to talk to B, what should I do? I should condition. But intuitively, if I want A to talk to B, I don't want A to talk to B, what should I do? I shouldn't do anything. Okay, so here, if there is an unshielded collider, don't do anything, don't condition. If it's here, condition. Okay, so this basically defines D separation. So it's always good to define D separation by its complement, unfortunately. So you first say what is D connection, and then you say whenever it's not connected, then you say it's D separation. Okay, so let's do a contrapositive definition. So definition of D connection. Now the D connection, it can be specified with respect to every path, right? So suppose X and Y are deconnected. So okay, so X and Y are deconnected. Condition on Z. When will it ever talk, right? Whenever it's not a collider, right? I should not be conditioning on it, right? So suppose there exists. So if there exists a path P such that suppose some member of any non-collider in P does not belong to Z. That's it. The non-collider is simply defined with respect to whether the arrows follow this pattern or they both point to this pattern.
That is called a collider.
This is called a collider. Okay. So non-collider in P should not belong to Z. Because will block it, this part, right? Yeah. And if there exists a path where this happens, and all colliders in a P. So I want connection. So if I only condition, will this be connected? And all colliders in P should belong to Z, or all descendants of some descendant of a collider does not belong to Z. Sorry. Complicated definition. So all that's saying is, if X and Y are deconnected given Z, if there exists a path such that all the non-colliders in P does not belong to Z, all colliders in P belong to Z, or some descendant of a collider belongs to Z. You take every collider here, check two conditions. It itself should belong to Z, or some descendant of it should belong to Z. Why is this a more nuanced condition? Suppose you have A, B, and C.
Is undirected.
What?
We are looking at a path that is undirected.
No, any path it's a directed path.
Then how can it have?
So it's a oriented.
So oriented path. Okay, take the skeleton.
Yes.
You have a path.
Yes.
Let's say non-repeating.
Yes.
Then go to the graph and just borrow the orientation. Okay. In that, if there is any, so all variables are either colliders or non-colliders. Clear, right? Because they have to follow one of them.
Yes.
For sure. Then all the non-colliders should not belong to Z. And for every collider, either that must belong to C or some descendant of it should belong to C. So for all colliders, either that or some descendant should belong to C.
The collider here is C. Let's look at this.
Yes.
And we want to not condition.
Yes. No. I want a condition because I want to connect.
Want, do not want independent.
Yeah, we'll come to the complement later. Yeah. So D connection means there is some path such that no collider belongs to Z, and all colliders, one of the conditions to either that itself belongs to Z or one of its descendant belongs to Z. So why is the second condition? Let me tell you. So even if I condition here, it's like conditioning the ancestor, and therefore you're again allowing these to talk. Okay. I mean, you can check this. I mean, I haven't proven any of this formally, but this is easy to check. For example, for a deterministic function, 1-to-1, if I condition on D, it's equivalent to conditional. It's an intuitive way of thinking. Yes.
I'll just silly question.
No, the definition.
Why is it called a D connection?
I mean, for the reason why it's called D separation. It's a DAG version of the separation and connection. That's why it's called D.
I was thinking it's D connection.
No. It's just DAG connection, DAG separability. It's a graphical property. Every path will have this property or not.
Okay. And this is for some path.
Yeah. So in order to make the definition a bit more clear,
every path is either active or inactive. Active means it is carrying information and active.
yeah. So X and Y are deconnected given Z by path P or active if this is true. It allows you to talk. Right? All barriers of disconnection should not be there. That's how it's. Yes.
So it's and or A and
This is necessary. This is also necessary.
A and B or C.
No, A and B. So A and B. B has two conditions, either or not, for every collider.
Why did you assume DAG in the first place? Like for all these steps?
I only assumed ordering. I haven't said anything about it.
If G should be DAG.
Yeah, because I always have a factorization with respect to some order. There's nothing causal yet. I'm not implying any causality among the things yet. But any distribution, you can always parameterize by it because of the conditional. I mean, why not have some other theory? Sure, we can, but we'll come to that later about feedback loops and all that. But that's you are giving a causal interpretation already. I'm not giving anything yet. I'm just talking about factorization.
Conditioning switches the arrow. So the first two figures, right? In fact, the first three are very sort of in line with the mnemonic that you're using, that you want A and B to talk, which is like A and B being dependent.
Yeah.
First figure, for example, is exceptionally good because A information is flowing to B, B information is flowing to A. So you don't want to touch it. Right? So that really says that any non-collider should not.
Well, if you want this path to be the connecting.
Yeah. Three also has a thing that there is some communication happening. So again, you don't want C to be.
Yeah, if they're already independent,
yeah.
If there's a common collider, unless you condition on them, they won't become dependent.
Yeah.
So you don't want to introduce such collider. This is called collider bias. This is a very famous thing actually. This is called collider bias. And by the way, again, going back to Reichenbach's principle, up to mediators, this is also Reichenbach's principle.
The mnemonic way to sort of remembering C connection, that once you condition on C, the arrows change their.
I would say remember all three, remember all four. This is the easiest way, and this is how it's defined, this is how it's motivated. Then an easier way to remember, I don't know. If you're in this business for long enough, I think it's second nature. That's really all I can. In my opinion, think of D connection and say D separation is when no path satisfies D connection, then it is D. That's a much easier way to. Always think of the contour because the other one is complicated. Okay, because you have to say something for all paths and all that, and it's very weird. So D-separation is when there exists no path B which connects. You know what? I'll write it there. Important. So D-separation is no path B connects X and Y given. So the given Z is like conditioning, but it's always defined given Z. It's a triplet. Yes.
So polytime test.
Polytime test. No. Well, it depends on what you mean by polytime test. In what parameters of the graph? If the graph is sparse, want to check.
Because like I give you X, Y, and Z. So every vertex, whether it's a collider or not, is now done. So
is the question given a graph?
given a graph, X, Y, is it D connect?
That you can use the other thing. So if they are de-separated, they are definitely de-separated by their own patterns. So if you knew the graph, so what I'm saying, suppose there was a de-separation. Okay, it immediately implies first of all X. This is not true. Neither this holds. Because if I have a directed path, it satisfies this condition. Right? Condition on the Z, I mean, you have to worry about Z conditioning or not, now that very clearly. But if you only want to check if X and Y have some Z which de-separates them, then it is very easy. Some Z. But if you want any Z, then I think you need to really enumerate all paths, I think. But there are alternate definitions involving moralization. I'm not so sure complexity wise it would make any difference, but I think testing is a problem. Because minimal de-separation sets and all that is very difficult.
Yeah, but this is a computational thing very easy, but not easy.
But you have to enumerate over all paths, right? That's what he's asking.
Yeah, but it is not clear right away if there is an efficient in the number of
nodes. I am not so sure. That's what I'm saying.
For given path, yes.
Yeah.
So, but you have to check for all paths.
Exactly, that's the point.
But if you want to check, I mean, a more useful question, I think, in causality is that can you find any Z that will de-separate X and Y? Because that's what usually is used for discovery.
Okay.
If you want to answer that question, then that is very simple. Because if that were to hold, first of all, there should be no edge at all. In which case, if there is no edge, I already told you the Reichen-Bach principle, which is X and Y are always independent of parent of X times parent of Y.
Series of X and Y.
Yes, if this does not hold for it, no other Z would definitely work for it, for sure. Right, which means there is a direct path between it, there is a direct edge between it. So that you can actually test, right? But you cannot easily test a specific Z, it's not very easy. But there are, okay, so what's the minimal de-separating set between X and Y? People have studied it. And they have some non-trivial things to say, but I'm not so sure. I can't recall the results to say whether they are. I'm sure they're exponential in the degree, poly, and most likely it's what it is. But anything more, I don't know. Maybe there are efficient ways of doing.
So if you assume some, to answer this question, if you assume some sparse structure, this one, then the number of, you just want to reduce the number of paths to poly.
Then like, just think of like the diamond E-drew, right? Like just keep attaching the
Exponentially many paths.
Degree 2 graph.
The second question is this true, like condition number 2, exists a collider, or the first condition is for all non-collider? Second,
but for that you can decompose and then only take that. But I don't know how it's general way.
Yeah. So second condition is exists or
For what?
condition 2?
Yeah, for
all colliders, either that or its descendant must belong to.
And the first condition is also for all non-colliders.
For all non-colliders, because it's a path I'm testing. In the path, both conditions, if either of them is violated, then it will basically connect. Okay, now yeah. So okay, deseparation. The most important theorem is that why am I doing all of this? If you find x and y deseparated conditions on Z, it implies conditional impact. That's why I'm doing all of this. Okay, that's very important. That's the most important. I have 10 minutes. At least I need to get to concentration. So let me do that. Because I was hoping I will use this to prove backdoor adjustment. But I guess that's the wait. Right? Okay.
So it's good.
Sure. Okay. Causal Bayesian net. Okay, there's one more property I did not say. When are two graphs Markov equivalent? I didn't go there, but that we will go there when we get to discovery parts. Okay, I won't go there right now. Okay. So causal Bayesian networks. Again, this definition is basically making the Bayesian network causal. Like, what should you assume more about the Bayesian network such that you have a causal interpretation for ordering and locality? Right? That is what we are going to define. Now, out of this comes a very important principle called invariance. Usually, people define it in one way, and then they show that it implies invariance. I won't go through the pain of doing it. It's just mostly math, like just shunting around factorizations. It's not some very deep result. If I say it, you can prove it yourself. So I'll just state it as two different definitions. Very good. Okay. So what is a causal Bayesian network? Now, I told you that the notion of causality is very almost inseparable from the notion of an intervention. Right. So I have to define what are called interventional distributions. So I'll call them P of B. These are interventional distributions. So let me actually check T is equal to T, which means I take a subset of those nodes, I set them to a very specific value T. Okay. This is a definition. I haven't told you anything about it yet. Okay. So these are called interventional distributions. Okay, this is an interventional distribution. I mean, with respect to the set T, and it is set to small t, essentially. I'm not going to define any do calculus yet. I'm trying to figure out if I can do it without that. Let's see. Okay. Now, you have a class of distributions called the interventional class. It's if you have discrete data set, it's countably many. But if you have continuous, it's uncountable, right? And this is nothing but the family of PT of V for all T is a subset of V, and for all T in the domain. You just consider something to be a domain and then you define it. So this is P star. Okay. This is all definitions. There is nothing I've said about any of them. Okay. Now, the notion of a causal Bayesian network is a common set of Markovity conditions that ties together different distributions that are parameterized by subsets and them being set to some specific fixed values. Okay, that's all there is definition. It's basically a coupling. And I am basically defining what the coupling is. Okay, so this family, so there is a G. We'll come to that, right? So you can say that P star is compatible with G, which means it's a causal Bayesian network which is Markov with respect to P star, or it's compatible with P star, if note already I'm creating a family. Okay, I'm not defining it with respect to a single distribution. It's always defined with respect to a bunch of interventional distributions. So this already points to my earlier comment. It's very difficult to separate the notion of intervention and causality. Okay, this is one way of doing it. And there are equivalent ways, but this is the cleanest way that I know, and this is the usual definition adopted. Okay. Now, the first criterion. Okay, by the way, it also includes observational distribution. Okay. So when T is null, basically it's the observational distribution, something like that, right? So P of B is equal to P null. Okay, when you don't intervene, it has a special status observation. Now, so what's the first criterion? The first criterion is that PT of B is Markov with respect to G. Okay, this is the first criterion. LMS. With respect to G. So this is the first criterion. This is for all. From this family, you take any one of them, it should be locally Markov with respect to G. That's the first criterion. Yes.
But the intervention distribution might.
It might be Markov with respect to a sparser graph, if that's what you're trying to say. But it's always Markov with respect to the denser one, even if you cut off edges. That's the minimal, because I'm taking all interventional distributions, including the observational one. So if at all it has to be marked out to some common graph, we might as well start with the original.
So interventions only create additional conditional intervention.
Yes, the definition implies all you are saying, but the definition is very just this. But it corresponds to you cutting edges off. Okay. Okay. What is the second criterion? I have to explicitly define what PT of B is. So first of all, PT of B. A bit of a complicated definition, so let me do it. So when T does not, when X does not belong to B, those conditionals will remain the same. Okay, so you have basically Xi that does not belong into T, doesn't belong to the interventional set. Those guys will just remain the same. Okay. Now, it is equal to 0. So this is actually the full definition, but the only important thing is you want to make sure. So this is a joint distribution over B. Okay. You want to make sure T is the small t is consistent with this B. Okay. So T is consistent with B. The interventional part must be the same numbers as these things. Right? If you intervene on T1 is equal to 3, T2 is equal to 2, but you are looking at the joint distribution with respect to two other variables, then it doesn't make sense. Right? But if it is not consistent, then it is equal to 0. T is not consistent. Why? Because if I force these values, this particular T cannot take any other value, right? I mean, because I'm forcing it. This might look like more like a pathological case handling, but this actually defines the notion of an intervention. So this basically defines this is called the group distribution. So we have a different name for it. Call it P of B given to P. That's what this means. This is like any other joint distribution. If you integrate it, this will actually become 1. Okay? Because you are just taking out all the things where this is not consistent.
Just like an indicator function, right?
Yes, it's an indicator when T is consistent. Correct, perfect. That's another way of stating it, but I take care of this. Okay. Is it clear? So here I am giving you a very different interpretation of the local Markov condition. I'm saying when I intervene on anything else, if I don't belong to the interventional set, my conditional distribution remains as it is, and it's equivalent to the observational one. The observational one has all the conditionals. It's the only thing that has all the conditionals. Any other thing will miss some of the conditionals, but what it will miss depends on where I'm interviewing. That's it. It's a very simple modular term. So this gives rise to what is called the modularity principle. Some people call it invariance principle. I wrote it in a paper. People had objections because there is another invariance principle. So I'll use modularity as a thing. So this immediately points out that the conditional distributions act like a module. They are always there unless you disturb them. And in reality, also in some ways works like this. Unless you go and disturb something, its parental influence on that will remain the same. And that is a usual notion of causality. Right? This definition captures all the, so this also captures the fact that when something is intervened, you basically cut off the parents and you set the variable to something. That's exactly all that happens.
So causal Bayesian network has two things. One is graph and family of
Interventional distributions for all subjects.
For all subjects, for all
Small keys. Yes.
Not still following when the second condition
So these two are, there's a definition.
is 0 pi.
So when T is, so see, the thing is, I'm evaluating the joint distribution on a sequence. But let's say T is the first variable and you have set it to 0. Does it make sense to evaluate an interventional distribution where I set the first variable to 0 on something where the first variable is something else like 1 or 2? No, right? If I force that variable to treatment, it cannot be controlled. That's what the consistency is. Very important. This basically reminds you that you're forced that variable.
How is it different from conditional distribution?
What do you mean?
The two operation is different from just conditioning on the.
You're not like the final condition. You're not multiplying by the probability that capacity will be equal to this. Leaving that out as one. It's somewhat critical.
Yes, this is not correct. You check it out, but it's not correct.
It is just that you are not multiplying.
I mean, quote unquote, just but you know. So you are saying because something is consistent, you are basically saying why is this not same as conditional distribution? The problem is there will be other factors that will get conditioned on basically T. That's what I'm saying. You have to normalize by all the things where T is equal and no normalization. They're all removed out of the picture. Whenever you intervene on something, they're just off. The rest of the conditional distribution alone remains. But if you are conditioning, you have to set that equal to 1, but still condition on its parents, and there is a conditional probability there. So you have to divide by all of those, essentially. So, okay, the conditional probability distribution will look like this. P of D given T is equal to D. We'll actually look at all the things where Xi does not belong into T. This will hold. That I completed D, but something else will also hold. It has to multiply with all the Xi's that belong to T. Then you set P of Xi is equal to T, conditioned on its parents won't go anywhere. Then divided by summation, divided by all the summations over B such that this is true. You need this. And you just need to sum over everything actually. All B you have to sum over everything. This is a very complicated distribution. Right? I am just saying none of this exists. Just the things that are not disturbed, they only remain. Everything else is. So now you see, right, the interventional distributions appear to be simpler than the conditional distributions. Right? So it's a very powerful thing. You just knock off all other modules. But here you don't do that. You just do some very complicated normalization. Yes.
So what you're saying is you can obtain this two distribution.
Yeah.
From
Yeah, I need the other one. Just need to condition on the fact that Xi is equal. And you have to take all these such that this is true. Right? Only then it's a condition. I am saying all this factor, normalization, nothing exists. It's only this. That's all.
So the root distribution is effectively obtainable from the joint distribution dividing by
If you knew the joint distribution, yes, you can always obtain it.
dividing by the correct.
Correct. Okay, is that clear? Okay, so that's a definition of causal Bayesian network. There's one more important property, which is the modularity. I'll stop with that. And then from next class, we'll continue more. I mean, there's just more theory to develop. So we'll do that.
The non-causal Bayesian network is a single distribution and conditional independence is implied by it.
Exactly.
We say causal, it's actually not, it's a family of distributions. Particular base distributions and multiple distributions.
Correct. Now, some people are not very comfortable with writing an explicit factorization to define causal Bayesian networks. Okay, so there's a very beautiful paper called Local Characterization of Causal Bayesian Networks, where they showed that this is nothing but another bunch of conditional independent statements, but it has to be stated in an appropriate way, giving rise to what's called modularity. I'll tell you what modularity is. I mean, that's your opinion. If you want, I can invite my friends from statistics and then they'll try to convince you that it's not me.
Yeah, sure, I'll get convinced. I start with then define a graph and then define.
Okay, I think one person feels that this should have come before. This is the main point for me to actually go through all the potential outcomes and then come to this, so that you get an understanding of why this is. Right? Okay, so the other thing is the modularity condition. This is a very powerful tool, at least in whatever the limited knowledge that I have about this business. This is not implied by anything I know in potential outcome, unless you want to optimize imposing using this condition. It's not ab initio guarantee. Okay, so these conditional distributions have a special name. They are called causal mechanisms. These are only specific conditional distributions from that ordering and from that graph. If I take any other conditional distribution, they are not going to remain invariant. What do I mean by that? So let's define a new independence. So conditional independence have always been about taking a bunch of random variables, basically saying that some random variable and another random variable is independent conditioned on something, right? Now we are going to go to a slightly different level of conditional independence, where we are going to talk about conditional distributions across distributions. Okay, so what does that mean? So I need some notation. So I'll say X is independent of Y, conditioned on Z, P star. No, so let me. Let me actually say that is invariant with respect to P star. Let's not complicate this. Okay, what do I mean by that? There are now two set of variables, X and Z. I'm saying that there's a new definition, invariant with respect to P star. So what does it mean? Now what you do is that you take P1 and you take P2 on both sides. Okay, both belonging to P star. They are interventional distributions. Okay, when you check the identity, P1 of X given Z is equal to P2 of X given Z, or not. If it holds for any two, so for all P1, P2 and P star, if this conditional independence holds, or it's not conditional independence, it's actually equality of two conditional distributions. If they actually hold, then I call X given Z is invariant with respect to P star. Distribution. distribution from the family. Now, with respect to one, I take conditional distribution. With respect to the other, I take conditional distribution. I ask when these two conditional distributions will be the same. Okay, if they are, then you call X given Z invariant with respect to P star. Yes. I think X and Z are subsets of so X and Z are subsets of V, right?
So I can intervene on X in P1.
This is a definition. So this is nothing. This is just a definition.
I'm asking what if you intervene on X in P1 and in P2 you don't intervene on X, so this will never be set for all P1.
Correct. But this is a definition. Now, like you pointed out, I need to qualify the definition a little bit more. So what I will do is I'll just make sure that X is not in P. You're right. So if I intervene on X itself and set it to two different numbers, this will never hold. Right, so that's true. So I have to get rid of that condition. So I have to make sure that find two distributions from P star such that this X is not belonging to T. Then check with any other. Yeah, I mean this is P of P1. This is P of P2 because I have parameterized by P star with respect to all subsets T. So it's implied, but if you wanted to be very explicit, I'll just write it as P1 and P2. And I want to make sure that X does not belong to either of those. Yes. Then X is said to be X given Z is said to be invariant. This relationship is said to be invariant. That's all I have defined. So definition. Now, very interestingly, 2 is, or at least, 2 can be replaced by the following very simple theorem that for all xi, right, xi given PA of I invariant with respect to P star, by which I mean exclude those things that xi does not belong to. By the way, when I have equality between any two pairs over all distributions, it's just equality everywhere. So it's just literally it's the same conditional distribution. Okay. So what we are saying is for every xi, right, this is invariant with respect to P star. Okay. You can think a little bit about it. You can actually show that these are the only things that are invariant with respect to P. Nothing else exists. Okay. Now, this goes back to the question that was asked before. If P is Lm with respect to G, there's always some other G for which with respect to which local Markov condition also holds. But this is a super sum condition. This says if this factorization were to hold in all interventional distributions, then the only conditionals that will remain throughout my family when you don't intervene on xi, it's important, is this xi given PAI. Any other conditional distribution will be different at some interventional distribution. Right? So this defines the cause. Right? This module is acting like a causal mechanism. Equivalent to this, by the way. Not obvious, but it is.
The definition of the modularity that you see distribution is being equal.
Conditional distribution. For z equals z, this is f of z. This is z equals z, this is f of z. I'm saying that these two functions are the same for every z across these two distributions. To take another conditional distribution, they are the same. That's why I didn't want to go into measure theoretic things. Discrete probability is easier to say, otherwise it's too complicated. Oh, yeah, okay.
Interestingly, Z can belong to P1 or P2.
Yes. You can intervene on the parents, no problem. Still the module is the same. Right? It's very correct approximation, but these two are equivalent. So you have a descriptional view of causal Bayesian network. You have a purely conditional, I won't call it conditional, invariance view of causal Bayesian network. Because the only modules that come out as invariant are these things. There's nothing else that stays constant. Every other conditional distribution is bound to change in one or the other interventional distribution. Maybe that you haven't seen enough, so that's okay. But if you get to ever see all the diverse interventional distributions, this is the only thing that will remain, nothing else. Yes.
Come out, these should satisfy invariance, like given P of X. But there can be other.
No, there are none. This is the definition. There will be only one. You see, right? I'm mutilating that one or the other in any one of the distributions, right? I can always mutilate any one of the x's and just throw them away. So in that particular distribution, if you try to look for this, you won't have that.
I cannot create like
T1 is equal to T2 is equal to Z.
T1 is equal to T, mean you are intervening on the same set.
Yeah, but I'm changing the domain. Changing the value I'm going to.
Yeah, you can.
Then one will be inconsistent, another will be consistent. And make one distinct.
No, but the conditional distribution. See, the only okay. It is true that the conditional distribution may not be realized by something, right? But what I'm trying to say here is consistency is defined only with respect to the intervened variables over here. So it will be zero in the other cases.
So the T1,
The conditional distribution doesn't change. Its realizability will change. Yes, true. I can always write it as I know what you're asking. If one of the PAYs had a different T, it doesn't appear at all. So then how can you actually define it? But still conditional distribution can be defined to be that without any loss of generality. That sense, this will be, yeah, I know that one of them is not even like realized. That's true. But of course, this makes sense only if, okay, one more thing I want to say is that when X and Z, I say, you have to make sure X and Z are consistent with respect to T1 and T2. Otherwise, you get into such issues. Okay, maybe I should be more careful. So X is, sorry, T1, T2 are consistent with respect to X comma Z. Meaning if they ever belong to T or, I mean, X doesn't belong to T1, but it could belong to Z, you make sure you condition on those things which are consistent with respect to T1. If they are not, just don't.
how is it?
No. These two are separate. This is not enough.
And T2 is by itself.
2 by itself is also not enough. Why is that not enough?
I was sort of using it to define like PA of I is like, even like
At least what I know is that you can't get this condition. I'm trying to see if this definition includes a part of 2. I guess if you have factorization like this, it automatically implies 1. You're right. Yes, I am being superfluous, but this does not necessarily. So if I have this condition, then 1 and 2 need to be stated separately. You're right. That 2 already includes 1 in the first place. You're right. But people state 1 and this as one kind of condition. There is one more condition that I want to say is that okay, there are many equivalent conditions. Let's not get to that. This is good enough for now, like for modularity. There are many equivalent conditions. So this is in the local characterization of Bayesian networks paper. They actually prove. But you're right. 2 automatically implies 1. Yeah, it's just yes.
First characterization of the do calculus of the graph. The second was the set of P star. The third is the set of all invariant.
Correct.
And all of them are.
No. So 1 plus 2, I mean, redundant 2 is redundant, but still 1 plus 2 is equivalent to 1 plus modularity. That's all. If you don't like explicit descriptions, you can define with respect to invariances. That's all of that. Yes.
To understand the edge case, so in the definition, at least you have not mentioned that there can't be other like xi commas, zi pairs where it still belongs to the invariant set.
Subset I have not considered because I'm not so sure.
No, not subset.
Yes.
Xi being a variable and some other set then.
Yes.
That can also still belong to the set, but it like
It'll get wiped out when you consider some other intervention. That's my claim.
necessarily, right? Like, because you can always have like 3 variables x, y, z, and even after conditioning on y, x and z are independent. It does also be.
No, but here there's no independent, right? Here saying conditional distributions are identical. It's not an independent statement. That's not clear.
I am wondering. So it's like deseparation implies independence, but independence does not imply deseparation.
Correct, but here we are not talking about the independence here. Here we are saying one conditional distribution is identical across domains. Yes, it's some sort of a meta-conditional independence when you pool all the data together, but that's a different interpretation. But all I have said so far here is that conditional distribution here and another conditional distribution there are identical or not. That's all I'm asking. I'm not yet told why it's can be realized by another CI statement. That will bring me to the proof of Dugan. Yeah, so we'll come to that later.
So again, going back, CBN is the set of all P stars.
CBN is a set of all P stars compatible with a G in the following sense.
Right. G is the set of all conditional, all the set of conditional independence.
No, G is just parents of every I. Once you give that tag, yeah.
And this modularity condition is the set of all such X parent.
Xi given some Z. I am claiming the only C that can satisfy this is parents, nothing else.
Well, now there is anything that I need to assume that anywhere here or
Yeah, right. Parents of I and I relationship, there is a tag, right?
But
parents of I can exist in cities also. It can be weird.
No, but this is a tag.
Yeah.
Yeah, otherwise the equivalence is not. This is only defined for a tag.
Defined for a tag. But for cyclic ones, you need to do something.
Yeah, we need to figure out what does it mean, like this factorization and all this not good. Because when you have feedbacks, I don't know how you will define factorizations. Right? It has to be consistent with the fact that there is a feedback. Then you need to go to structural causal models, and there's a way to do it. Yeah. There are people who study it, but that's not.
You need a structural causal model
for that.
For cyclic graphs. Otherwise, you cannot do it.
At least as far as I know, I have not seen a definition without it. But the good thing about this is that it doesn't need any structural causal. I haven't yet introduced to you what structural causal model is. I went to Bayesian networks, did some connections between D-separation and conditional independence. And then I said, okay, now let's consider all distributions together. Now these local properties are much more general. That's all I've said. I have not said anything else. That's clear? Yes.
But for this condition, you didn't need the graph. You just took, you could possibly find this with respect to some set of variables.
But there is an I and PA of I, right? I said for all except already defining a graph. I mean, the cyclicity part, I have to explicitly post. Yeah, I am considering a tag, but the structure of the tag is given here. Yes. This is a definition. P star G are given. Then what all you need to satisfy so that this can be considered causal. I'm just telling you what the criteria are.
For each person, you are telling all experience. So graph
yeah, adjacency matrix is you. Directed, the upper triangular version.
So if you find this with respect to data, you get a unique tag.
Yes, if you could verify this. In fact, there's a paper called Invariant Causal Prediction by Jonas Peters. They literally use this to learn the tag. So they do regression and they look at when the regression coefficients change. And they try to find that subset where it won't change. and in the limit, they know you will get the balance. Right? And that's the invariant causal prediction paper. It's a very famous PMES paper that started a lot of things on invariance. Right? So if you want to know that these are causal parents, this basically tells you what tests you need to do. You just need to make sure this regression coefficients are the same across all interventional distributions. So if you find an invariant relationship, then it is causal in the limit. And that's the only definition of causality. There is nothing else apart from the ordering. This actually has some ordering information. Rather than that, that's it.
The set of conditional independencies is actually not giving unique graphs, but this does. So
This does.
Stronger.
Exact, stronger. So then okay. Now comes to the open question. We went a little bit far to this open question, but we haven't fully solved it. Okay, open question. A lot of variance. It relates to interventional design also. What is this saying? This is saying I have to consider my entire family of interventional distributions and then look for invariance, and only then I'll know that this is a G. Right? Now the question really is, under some other assumption, can you do better? Do I really need to look at all the interventional distributions, which means I need to intervene on all subsets, at least minimally, and before that I make any conclusion about the graph? That's what the definition says. But the question is, how many do you need? Right? So the first question is non-adaptive. How many tests? How many members of P star do you need before I can uniquely find the graph? Right? So Kiran here has done a lot of work on that, and he will tell you that it's not all of P star, at least first class graphs. Right?
So you promised that not written in this language.
Yeah. No, but it implies precisely this thing. Like, how many interventions do you need to do before you can actually get basically members of P star? But there's an assumption involved in all these words. The assumption is that the conditional independencies that you are testing and the invariances that you are testing are only implied by the structure. Okay, there are distributions that don't obey these conditions, for which none of these interventional complex fields are solved. Then the question is there some other observation model, maybe a random model or something, or how many random realizations of P star do you need before you can uniquely determine invariance? So we have a paper recently here to answer the question. We said that if you have P star and but only for linear SEMs, it can't work for non-linear models. So we don't know the full answer to that question. But if you randomly sample, you can actually show that n to the 4 environments are enough. And you might say, why n to the 4? It's neither 2 to the n nor non-linear in n or log n or something which is known before. We don't know the answer to the question, but there's a lot to be understood there.
So n to the 4 different
Random draws from P star.
P star, but now you like one of the element is like small t and one capital P is more than.
Yes.
You are characterizing the domain.
Yes.
Value you said.
Value set. In fact, we have a slightly weaker result. What we are showing is if an invariance holds, it will generalize with high probability. That's all we can say over the randomness over which you have drawn. So if you take any other random thing from P star, it will hold. I cannot say that it is causal because you can never say that unless you fully see all the interventional distribution. But what I can say is with very high probability, this invariance will hold. And depending on the distribution, it means whatever causal. I mean, that's all you can say in real life. All you can hope is whatever interventional distributions you have in your data, in your view, you can only test the conditional dependencies and check if they hold throughout. If they hold throughout, you're likely to believe that it is the causal model. That's all you can say. You cannot say anything more than that. So the reverse question is obviously a lot has been understood, which is if I give you a subset of P star, what is the equivalence class that you can get? We will come to that topic.
Can we try to?
Specific subset of P star under faithfulness assumption.
So I don't know how to think about small t. For us,
it was always randomized interventions.
Yeah.
Right.
Yeah.
Unfortunately, the definition is with respect to small t. I would like to say that you can randomize it and still the whole thing will hold. but I'm not too sure. That's why I'm not
So
committing to it.
the random draw you are doing from the start, it's like all T's
Correct.
have equal probability.
Correct.
No cardinality.
No cardinality.
Let's say you forget small t now.
Yes.
Can you say, whenever you pick a capital T, I'll give you all small t distribution.
Okay. You give all of them. Okay.
So then how many draws?
Then, I mean, I don't know. I'm just saying from even the random model, you need n to the 4. But only for testing invariance, which can hold in the test distribution is also a random draw. I'm only asking for generalization. And only for linear escape. There's a lot of conditions. So in general, I don't know how many. But what is interesting is that the definition requires 2 to the n. But you can make some statements like this. All right, and you can do approximate invariance and all that. So you can extend this theory. So basically, we use Botu's. I don't know if you are aware of the IRM paper. There's a regularizer. We take that to be the definition of approximate invariance. That regularizer being less than epsilon. So we ask our question: if I randomly draw P star, if that holds for these many, will it hold with a high probability on some new intervention that's going to come from the same family? For that, it is n to the 4, only for linear functions.
So now do you need to make this faithfulness as a
No. The randomness actually creates. So the fact that it's a linear STM helps a lot. It's actually a piggyback on VC theory. It's a very interesting way of looking at interventions as samples. And then you can easily write the regularizer suitably. It will become like a VC bounded model. And then you say that the samples are like the causal models that you're sampling from this interventional family. And then you can make you can do the argument. So we're able to do that. But in fact, people are worried, why is it n to the 4? Why is it not much smaller? Why is it not linear? Why don't you? Because the intuition is that if I truly want to learn the graph, if I intervene on every variable, I should be able to. But turns out that you need faithfulness for it. It's not very clear whether you can make that statement without faithfulness or how much of a statement can be. See, if I intervene on everything, I knock out one after the other, right? Everything else is remaining the same. So I get this diagonal pattern. So I'm reasonably convinced that these are my patterns. That's what everybody would say. But in order to test that, it seems like you need interventional predictions. In general, over any distribution, pathological distribution, is this sufficient? Not very. Is it clear or?
The faithfulness is not fitting for me in all these definitions.
No, I haven't even introduced faithfulness yet.
Yeah, but
So the point is that if you don't intervene on something, this conditional distribution must have some strength, meaning marginally Xi and PAI must be dependent. But there are models where they are not. Right? And when I'm saying I'm randomly drawing from P star, it could be one of those models. So when I'm talking about generalizability, I have to take into account that there are such models too. Or whatever your proof technique is has to handle such models indirectly or directly. And I don't know how to. In general, I don't know how to. So an example, okay, before I talk about things, so the very famous example people give, X and Y are Boolean variables. Bernoulli half. This is D. Okay. Now you can test yourself. This is a binary symmetric sample. I'm corrupting it with Bernoulli half noise.
What is C as a function?
X XOR Y. Plus you can have one more Bernoulli half noise if you want noise, but that's not important here. This is still a Bayesian network. Okay. But in this X to Y, there's a direct relationship. I literally constructed Z using this. Right. But remember, D separation only implies independencies. No deconnection does not imply dependency on all distribution. I have never made that claim. Okay. So here, X and Z, you can do the mutual information. If Y is actually Bernoulli half noise, it's like a binary symmetric channel with half switch probability, which means the mutual information is 0. You can't send any information in this channel from X to Z. We know that. Therefore, mutual information is testably 0. In fact, you might even change this Bernoulli half to something else. Still, it will hold. But only when you change this Bernoulli half to half minus epsilon and half plus epsilon, you will actually start getting dependence. Right? So there are weird models like this. And interventionally, okay, this is true, sure, but this could be 2 by chance also for some other model, for example. Right? But unless I see all my P stars, I can't be sure. You see, right? So there is this exclusion, there's some very weird distributions lurking in that. We have no idea how many of them there are, or in what sense will they affect your results, and so on. So these are called faithfulness violations, where there is an additional independency that is not implied by your structure. But such distributions are very rare because I change something about this model even a little bit, they are not stable. They have immediately become faithful, or that conditional independency anymore won't hold. Right? This is very important because the only way I can learn any of this is invariance or conditional dependency, all these mutual information going to zero things. But they must imply something necessarily about the structure. So learning is not in general possible for any arbitrary distribution, because I could give you a distribution like this. You think X and Z are independent, therefore there's no edge in the first place. Clearly not. Right? That's what you would conclude, but that's not true. Right? So it can be easily put off by such distributions. It doesn't come for free. But this definition is robust to all of that. It says for all P star, for all T consistent with this thing, I'll check. It's like a universe, right? Then, yeah, it's a very stable definition, right? But you will have such weird conditions that you always have to exclude, and we will come to faithfulness and all that like next class. I talk about it. Is this clear?
Yes. So when you said that you take n to the power 4 random like elements from this set.
For linear SEMs, it's true. It's not even true in general.
So one random instance consists of choosing a subset Z
And setting it to
and
X.
setting it to some random.
Right.
So the like, should it not depend on like some degree or?
So in general, it's under the 4. In fact, I am very surprised that it's even super linear in N. Because the intuition says that if you just hit every random variable, I should be able to test conditional independencies very easily. The reason that the logic will not hold is because here I'm not even intervening on Z, but conditional independency marginally is already 0. Okay, these are the only distributions that bother you. But the botheration seems to cause n to the. But by the way, all the statements I made is high probability statements. We randomly draw in the training, but you should also randomly draw in the test. Then with high probability, that will hold. The approximate variance.
Just to understand the definition, say my graph is x to y to z.
Okay.
A linear.
Yes. So let me erase that and you can tell me your example. Yes, x to y to z. Yes.
And z condition on y equal to 0 is same, like probability of z all up Bernoulli. So z equal to 0 condition on y equal to 0 is half.
Okay.
And z equal to 0 condition on y equal to 1 is also.
Okay. Y equal to 1.
Yeah.
Okay.
And everything is Bernoulli. Now
this is we are reading almost like an independent variable now.
yeah, so in that case, like now, like for now I define some conditional distribution.
But the point is, when you force, okay, so you're saying that how will you ever know the effect of y on z?
Yeah.
You may not know the effect, but the conditional distribution is the same is all I'm trying to say.
But like in the causal mechanism, now my set will also consist of x given, z given x.
Z given x.
So
But you haven't
this
said
is
anything
my
about
choice.
x, right?
So x I can just again choose half and half. The probability of x equal to 0 is half.
Okay, probability of x is equal to 0 is half, but this is important. What are you going to do about that? If you're going to make everything independent, then there's no edge.
But the model is still consistent, like my P star and this graph can still be consistent.
No, but if this is true, why is there an edge at all is my question. But nevertheless, this conditional distribution remains the same. So I'm trying to understand. So you're saying some other conditional distribution also holds. That's your main problem. Let's see. You're saying independent of what this is. So that I cannot agree because I can make probability of x is equal to y to be 1. Then you are in a different situation.
set of equations you gave is also consistent with Z2I.
So because I can force my X and Y to be two different quantities. Suppose this law was true, then already you will be breaking Z2X law. So whatever law existed between X and Y, I can intervene in a way that probability is sort of mismatched. Then it will affect the conditional distribution between Z and X because I have to marginalize over Y. I know that you have made this very nice, but there's a problem here. But you are saying that this also I can make it almost completely independent. But you are going to say now this is also probability of Y is equal to 0 given X is equal to 0 is half and X is equal to 1 is also half. Okay, so this is the distribution.
Independent.
All of them are marginally independent. So I'm trying to figure out.
With three independent variables, you can draw any graph you want. All of them are.
It is locally marked out with respect to any dense graph, but most important thing is also locally marked out with respect to the empty graph. But the question is, well, then what does the arrow mean actually? Because my point is that your invariance will be satisfied, but with respect to any, okay, so if you have an empty, okay, let's say you have X, Y, and Z. All this will show, I think, eventually, is that P of Z does not change. P of Y does not change, or P of X does not change, something like that. Then the graph that is consistent with all of this is the empty graph. So that will be your conservation.
Why would this graph not be consistent?
That's a good question. Let's see. My only problem is the dependence doesn't hold. Right.
Consistent.
No, but what he's saying is, see, but my only point is this invariance will hold with respect to the parent, but you are saying that even without the parents, it holds.
Yeah, like I can have some edge cases, there'll be some other Xi and some other Z. I can maybe construct such graphs and that will also be consistent to my P star.
No, but I'm a little bit, see, for example, if I intervene on Z and X, then I'm not so sure if the conditional dependency between Y and Z will hold and stuff like that. But in the independent graph, all of them will hold. So I know already a test that distinguishes between. I'm just saying I have a set of invariances that certainly distinguishes between these two. I am not so sure about the specific things that you're actually asking.
My question is just that.
Oh, this is the only, I claim that this is the only thing that will remain invariant. Here also you're saying that is remaining invariant. Okay, I have to think about it. So C given Y. But my only thing is this is almost an independent distribution. So there's no notion of a causal link there.
Yeah.
So that's what I'm trying to figure out. What does it mean?
About the definition, just to understand this, the causal mechanism, like this set is unique and is only consists of these elements. Should there be some more assumption like faithfulness or something to say that? Or
so as far as I know, this definition does not include faithfulness because it takes all P star. But here I'm trying to think: is there any configuration where you will have?
Wouldn't start like G is the complete graph. The tournament is
You are saying that this is just completely jointly independent distribution, right? Like this is independent of this is independent of this is already independent. So I'm having an empty graph at this point, but you are saying that you're insisting that G satisfies all my criteria. See, but that is not the definition that will be problematic. Even this definition is a problematic one because I can write my factorization with respect to G also. So I'm trying to see why this is not a causal Bayesian network. Good question.
I don't think so. We could have multiple G's for the same distribution. What is the
like given a P star, is G unique? Like,
I don't think so. Like G could always be the tournament and it will.
See, the problem is you have created in such a way that X and Z are independent, even though they're supposed to be a causal link, right? That's what really bothers me.
In faithfulness assumption is supposed to get rid of these cases.
No, but in the definition, you don't have, there's nothing about causal Bayesian is just a definition. This is causally compatible with respect to this graph.
And it guarantees unique G star.
G. Yeah, I believe so. I mean, at least that condition guarantees unique G, but he's asking if that is really the case, then you have these two edges. Technically speaking, there's no edge. I mean, if you just look at it, all of them are independent, like joint distribution is independent. But what he's saying is that still I will claim that this is my causal graph. But what sort of mechanism would give, so okay, maybe this is sort of related to the SEM question.
So, for my understanding, Xi given P A of I is invariant with respect to P star of G. But Xi given different P of I is also invariant with respect to P of G star I, G primeless. So, both are satisfied by this particular example. So, G and G star are valid.
So take that graph. P of Z is invariant under Y.
P of Z is invariant under Y.
Yes. P of Z is also invariant under X.
P of Z is invariant under X. Right. But
No,
you can't, it should not be, but he's saying it is.
So P star that you give me, you see that
Now, this violation is that this is the violation.
right, that is the violation. But I'm saying here, should it be for all Xi? Xi given parents of I are the only invariances. Is that the
Correct. Are the only invariants.
are the only invariances? And there cannot be any other invariance.
Yes, yes. That is the
So
important.
that is the definition. Then
Then this doesn't satisfy the definition, so this cannot be actually a causal graph. Yes, I think that would be the counter solution. But the question here is that our condition now will look stronger than the two condition, because the two condition is always satisfied. So he is just defining a conditional So my only problem with your conditional distribution is that this is equivalent to P of just Z is equal to 0. So why don't you write minimally like that is my question. But there is no minimality in the definition of the first factorization. The second one seems stronger. It seems to exclude this case. You agree now it excludes this case, right?
So by definition, now this is not a.
Yeah, that's what I meant. Yes.
But now, okay, again, like the equivalence of these, because the second condition that you've written, the factorization one, I think that is still.
That's what I'm thinking. This implies P of Z and Y are independent, but you insist on this conditional distribution. But you can always add no minimality. But that's a very interesting point, because I always thought that this was actually a weaker thing than that, and it needs some effort to prove it. But your example says it's actually stronger thing, but the 2 is actually bigger, because you need to be very clear about the minimality of G. Right? That's an interesting point.
Can define 2 always with respect to the complete some sort of use this.
No, but if you do that, the truncation formula is always right. So what he is asking is, I can always, I'm not disturbing the truncation formula. So in what sense am I violating a denser graph? That's exactly all he's asking. So that violates a denser graph. Sorry, that violates, the sponsor one. So you need, this violates the denser graph. That's what he pointed out. That's perfect. But the original truncation definition, which was supposed to be the thing, here it seems like I arbitrarily include anything I want which are independent. But then you are saying that also satisfies the truncation formula. So why can't I claim that that's a causal Bayesian network? Actually, the thing is, it won't change any of the interventional distribution. So I think you can still call the G, the definition doesn't say G is unique. All it says is that if there exists, so what I said here is it's equivalent. So you're saying that this is actually a stronger condition, which talks about minimality. Okay, so I need to look at the proof to see what is the issue. So you're saying one side there's no minimality. There's multiple graphs that can satisfy the same set of equations. The other side, there's only one unique graph that satisfies the equation, which is invariance. So this cannot be equivalent. That's what you're saying. Okay, so I'll check that and then come. Maybe G needs to be minimal in some, but I don't think there's any definition. It is true that this is the only invariant one. I'm trying to see if. But you are creating fake parents, right? Because they are not at all there. I mean, you're just creating. They can. I mean, you can never find a function where that is true, but you're actually creating fake parents. So I'm trying to see what is that again. But there's no faithfulness in the definition. Yeah. Okay, I'll come to that.
Even from let's say like just a counting argument as to the number of things, let's say the number of equations you have to test. This is a much more demanding. Like that is.
You have to estimate the conditional distributions, right, over all these stuff.
It's fine. I'm not saying in terms of this counts the number of equations that you have to look for. So it's not a testing or statistical.
Yeah.
It's counting the number of, in this definition, how many equalities showed up. Or like how many
formulas showed up.
This is much more. This is like
I thought this was easier to test because I don't care about the testing wise because I don't estimate anything. Like I don't check any factorization.
But like let's say I give you like I'm just saying if I list out data, that's one factorization for instantiation. This is see for every instantiation you have to choose this is quadratically more. Like,
okay, yeah, I mean they're just equivalent definitions. Right? There's only one unique object. But in fact, this seems to be tighter. That's what he's saying. I mean, this implies this, but he says that the left-hand side does not imply the right-hand side. That is very surprising to me.
So then the natural thing is you look at the sparses graph.
Yeah, then
might be unique.
That might be uniqueness. But
still now faithfulness will not follow. Right?
Yeah, it will not follow.
So,
but the definition for sure does not involve sparsity. You can look through the book also. I can tell you the book. The definition does not include sparsity.
So all the motivation I know for faithfulness is just to avoid these cancellations or the fake hits.
Correct, but CBN definitions do not involve faithfulness. Right? It just says that this graph is causal for me under all my interventional distributions. If these things is what I see, he is saying he's actually introducing fake bias and he's creating a denser graph. And he's saying, why can't I call this causal? That's what he's asking. But that you could do for any graph. So I think there is a minimality that is there. I'm just trying to see why that minimality does not work. Yes.
From my understanding, without the RD only part, you could get all we are suggesting is x to y to z is a valid graph. And then you choose a different xyz that is also a valid graph. So the point without the RD only is that unique graph is not obtained from this test.
No, this definition obtains unique graph. That's what he pointed out. The problem is the other definition, the truncation definition.
Without the RD only addition, it does not indicate it.
important part.
Oh, there's an important part you're saying. But the truncation formula is an ab initio definition. So I'm trying to see, but it doesn't say anything about uniqueness, but I guess that definition says that this is the unique graph. Yes, maybe that's what I need to qualify. But good observation. So let me, because you are just adding, you could just add anything you want, all my ancestors, and then claim that to be, because the conditional distribution is identical. So yes, it is a CBN in that sense. But you would be unnecessarily including parents. See, you are basically playing at the fact that there is a variable that's independent to me, but I will include that as my parent because I am very generous, which you can always do. But if you want minimality, I guess you should avoid that. So I must qualify here that this implies some minimality. So it's not exactly equivalent.
Factorization needs to be tight and like minimal itself.
There is no G smaller than that G for which it's possible. So that should imply a much stronger statement over. That is
Again, to the 4 result, is there a lower bound?
nobody knows. But see, that is under many conditions. Linear SEM are only under that, and approximate invariance. We are not testing for exact invariance. Qualified by a specific regularizer, we were able to prove all of this. But the question is generally that is open. And it also connects to interventional design, which is under faithfulness, we know all these results. But when I relax them, like where exactly I am is not. My guess is that under some structural causal model, which I have not introduced, some structural causal models, you should be able to get tighter results for 2 to the n. Instead of 2 to the n, you should have something much better. I mean, linear in n is supposed to be intuitive because if we intervene on everything, I have just figured out all causal relationships. But turns out from faithful, non-faithful distribution, that's not enough.
But note that if you allow me to intervene on higher cardinality cells,
Yes,
you
yes.
just need log n intervention.
True. You don't need, exactly. So that was another question people asked is you need only log n. For a problem for which you need log n, you guys are saying I need n to the 4 interventions. So why is there such a big gap? Just that I don't know.
But that log n is different. They are not counting small t's there.
Correct. That is
It is log n into some
yes,
small t.
small t. This is an old result from Peter Goldman. But that's a very interesting question. Adaptive version is even more interesting. So for that, do you need something lesser or order n? Not at all very clear. What? No, you are trying to find a unique
Not a
G.
testing question, right?
It is a testing question because I'm just getting more and more interventional distributions. When can you uniquely say that this is the G? There's no other G.
Okay.
Here we showed that it is a unique G. Right? I mean, once this is all satisfied, then there's a unique G, basically.
The testing problem is not each exercise, there's a candidate PAI for each exercise.
Yeah.
How many sort of draws you need to make from T star
Yes.
to sort of get them. And trivially, it would be quite a lot.
Yeah. The definition says you need all.
Yeah.
I'm just saying under faithfulness, we know you don't need all. You need log n. But if you allow only single node intervention, it's n. But there's an intermediate result where you can show some polynomial scale, but under specific assumptions. So there's a whole world of questions over here. How many do you need and under what conditions can you actually recover the unique G? Right. So that's the learnability.
Thank you.